Hello and welcome to the introductory lesson of the Apache Kafka developer course offered by Simplilearn. In this lesson, we will introduce you to the course. After completing this course, you will be able to describe the importance of big data, describe the fundamental concepts of Kafka, describe the architecture of Kafka, explain how to install and configure Kafka, explain how to use Kafka for real-time messaging. This training course provides information on big data fundamentals, real-time big data, Kafka origin and features, Kafka architecture and data model, Kafka installation, configuration, and monitoring, and interfaces to Kafka. The target audience for this course includes professionals aspiring for a career in big data, analytics professionals, research professionals, IT developers, testers, and project managers. It also includes students and those looking for a change in career. The prerequisites for this course include knowledge of any messaging system, basic knowledge of Java or any programming language. Some knowledge of Linux or Unix-based systems is desired. There are 5 lessons in this course. The table lists the lesson numbers along with the name of the lessons covered. This concludes course introduction. The next lesson is Big Data Overview. Hello and welcome to Lesson 1 of the Apache Kafka developer course offered by Simplilearn. This lesson provides an overview of big data. After completing this lesson, you will be able to describe big data, list the 3 V's of big data, list the various data sizes used for big data, describe Apache Hadoop, explain the concepts of real-time big data processing, list some tools that handle real-time big data. Digital data has exploded over the last 2 to 3 years. Facebook, Twitter, YouTube, and sensory networks have contributed to the rapid growth of data. Data volumes are measured in terms of millions of gigabytes. The technology has evolved to store, process, and analyze large volumes of data and to make decisions based on it. The technology to utilize large volumes of data represents big data. Big data is typically characterized by 3 V's. They are volume, velocity, and variety. The other characteristics include veracity, which refers to the truthfulness of data, visualization, value, and so on. Volume refers to data, which is the size of digital data. The impact of the internet and social media effect has resulted in the explosion of digital data. Data has grown from gigabytes to terabytes, petabytes, exabytes, and zettabytes. In 2008, the total data on the internet was 8 exabytes. It has exploded to 150 exabytes in 2011 and reached 670 exabytes in 2013, which calculates a growth rate of 20% a year. It is expected to exceed 7 zettabytes in the next 10 years. The table shows the various sizes used for big data. The size along with the power and description of each data term is given. The terms kilobyte, megabyte, and gigabyte are familiar. Terabyte is about 1,000 gigabytes, and petabyte is about 1,000 terabytes. The new terms added to address big data sizes are exabyte, zettabyte, and yottabyte. Typically, the term big data refers to data sizes in terms of terabytes or more. Velocity of data refers to the speed of data ingestion or data growth. Millions of web pages get added every day. Data also gets created from different sources such as desktops, laptops, mobiles, tablets, and sensors. Manufacturing facilities have thousands of sensors that generate data every few seconds. People use different devices to create data throughout the day. Due to the increase in the global customer base and transactions and interactions with customers, data created within an organization is growing along with external data. There are many contributors to data growth, such as web and social media, online billing systems, ERP implementations, network, and machines. Growth in the revenues of organizations indicate growth in data. Data variety refers to the types of data such as text, images, audio, video, XML, and HTML. There are 3 types of data. Structured data, where the data is represented in a tabular format. For example, MySQL databases. Semi-structured data, where the data does not have a formal data model. For example, XML files. Unstructured data, where there is no predefined data model. Data is defined at runtime. For example, text files. Industries such as transport, science, and finance add a variety of data every day. Digital data has evolved over 30 years, starting with unstructured data. Initially, data was created as plain text documents. Next, files were created. Data in spreadsheets increased the usage of digital computers. The introduction of relational databases revolutionized structured data as many organizations used it to create large amounts of structured data. Next, data expanded to data warehouses and storage area networks, or SANs, to handle large volumes of structured data. Then the concept of metadata was introduced to describe structured and semi-structured data. Finally, with the advent of social media such as Facebook and Twitter, unstructured data has exploded in the last few years. The images depict data evolution, starting with unstructured data through a structured database and ending with unstructured social media comments. Some of the features of big data are as follows. Big data is extremely fragmented due to the variety of data. It does not provide decisions. However, it can be used to make them. It includes both unstructured and structured data, where structured data extends and complements unstructured data. However, big data is not a substitute for structured data. Furthermore, since most of the information on the internet is available to anyone, it can be misused by antisocial elements. Big data is also wide. Therefore, there could be hundreds of fields in each line of data. Next, big data is dynamic, as gigabytes and terabytes of data are created every day. Finally, big data can be internal, generated within the organization, and external, generated on social media. Here are some industry examples of big data. In the retail sector, big data is used extensively for affinity detection and for performing market analysis. A retail company wants to find out the product Y, which the customer is most likely to buy after buying the product X. The company wants to place product Y next to product X to ensure the customer has a pleasant shopping experience. Credit card companies can detect fraudulent purchases quickly to alert customers. While giving loans, banks examine the private and public data of a customer to minimize risks. In medical diagnostics, doctors diagnose a patient's illness based on symptoms instead of intuition. Digital marketers need to process huge customer data to find effective marketing channels. Based on the last 20 to 30 years of stock market data, algorithmic trading can maximize profits on a portfolio. Insurance companies use big data to minimize insurance risks. An individual's driving data can be captured automatically and sent to the insurance company to calculate the premium for risky drivers. Manufacturing units and oil rigs have sensors that generate gigabits of data every day that are analyzed to reduce the risk of equipment failures. Advertisers use demographic data to identify the target audience. Terabytes and petabytes of data are analyzed in the field of genetics to design new models. Power grids analyze large amounts of historical and weather forecasting data to forecast power consumption. As data is available to the public, law enforcement officials must take necessary measures to detect misuse of data and prevent crimes. In traditional analytics method, analysts take a representative data sample to perform analysis and draw conclusions. Using big data technology, the entire dataset can be used instead of sample data. Big data analysis helps to find associations in data, predict future outcomes, and perform prescriptive analysis. The outcome of prescriptive analysis will be a definitive answer and not a probable answer. Big data analysis helps to take data-driven decisions instead of intuition-based decisions. It also helps organizations increase their safety standards, reduce maintenance costs, and prevent failures. Traditional technology can be compared with big data technology in the following ways. Traditional technology has a limit on scalability, whereas big data technology is highly scalable. Traditional technology uses highly parallel processors on a single machine, whereas big data technology uses distributed processing with multiple machines. In traditional technology, processors may be distributed with data in a single machine. However, in big data technology, the data is distributed to multiple machines. Traditional technology depends on high-end expensive hardware that costs more than $40,000 per terabyte. On the other hand, big data technology leverages commodity hardware that costs less than $5,000 per terabyte. Traditional technology uses storage technologies such as SAN, whereas big data technology uses distributed data with data redundancy. The cost factor is important for chief technology officers or CTOs and chief executive officers or CEOs to lean towards big data technology. In computing, a stream represents a continuous sequence of bytes of data. It is produced by one program and consumed by another. It is consumed in first-in, first-out sequence. For example, if 1, 2, 3, 4, 5 is produced by one program, another program consumes it in the order 1, 2, 3, 4, 5 only. It can be bounded or unbounded. Bounded means that the data is limited. Unbounded means that there is no limit. The producer will keep producing data till it runs, and consumer will keep consuming the data. A Linux pipe is an example of a stream. The Linux command is cat log file vertical bar wc-l. In this command, cat log file produces a stream that is consumed by wc-l to display the number of lines in that file. Apache Hadoop is the most popular framework for big data processing. It has two core components. They are Hadoop Distributed File System, or HDFS, and MapReduce. It uses HDFS to distribute the data into multiple machines, and MapReduce to distribute the process to multiple machines. It uses the principle of moving processing to data instead of data to processing. First, HDFS divides the data into multiple sets, such as data 1, data 2, and data 3. Next, MapReduce distributes the data sets to multiple machines, such as CPU 1, CPU 2, and CPU 3. Finally, processing is completed by the CPUs of each machine where the data is stored. So CPU 1 processes data 1, CPU 2 processes data 2, and CPU 3 processes data 3. HDFS is the storage component of Hadoop, which stores each file as blocks, with a default block size of 64 megabytes. This is larger than the block size on Windows, which is 1K or 4K. HDFS is a write-only, read-many-times form of file system, which is also called worm. Blocks are replicated across nodes in a cluster. HDFS provides 3 default replication copies. The image illustrates the concept. For example, a 320 megabyte file is stored into HDFS. The file is divided into 5 blocks, each of size 64 megabytes, as 64 multiplied by 5 is 320. If there are 5 nodes in the cluster, each block is replicated to make 3 copies, to result in a total of 15 blocks. These blocks are further distributed to the 5 nodes so that no 2 replicas of the same block are on the same node. MapReduce is the processing framework of Hadoop. It provides highly fault-tolerant distributed processing of the data by HDFS. It consists of 2 types of tasks. Mappers are tasks that run in parallel on different nodes of the cluster and process the data blocks. Maps are actually key-value pairs. After the completion of map tasks, results are gathered and aggregated by the reduced tasks of MapReduce. Reduce is used to summarize and consolidate. Reducers give the final output of MapReduce. Each mapper runs on the data block on that node. Data locality is preferred. This follows the paradigm of taking the process to the data. Some of the tools to handle big data in real time are as follows: Apache Kafka, Apache Storm, Apache Spark, Apache Cassandra, Apache HBase. Kafka is a high-performance real-time messaging system. It is an open-source tool and is a part of Apache projects. It provides a distributed and partitioned messaging system that is highly fault-tolerant. It can process millions of messages per second and send the messages to many receivers. Storm is a real-time stream processing system. It is an open-source tool and is a part of Apache projects. It provides fast and reliable processing of big data. It can process unbounded streams that sends data to Storm continuously. It can interface with messaging queues such as Kafka to get input message data and store the received data into a real-time big data database such as Cassandra. Apache Spark is considered to be the next generation MapReduce. It is also an Apache open source project. It is used to transform distributed data. It provides data transforms beyond map and reduce. It processes data faster than Hadoop MapReduce. When entire data fits in memory, Spark is found to be 100 times faster than Hadoop MapReduce, whereas in other cases, it is found to be at least 10 times faster. Spark is suitable for batch and real-time processing. It provides Spark SQL for SQL interface to big data. It provides built-in libraries for machine learning and graph processing. Machine learning consists of programs that can learn based on the data without being explicitly programmed. A graph is a set of nodes and edges connecting these nodes. Graph processing consists of algorithm to process the nodes and edges of a graph. Cassandra is an Apache open-source NoSQL database with the following characteristics. It is highly fault-tolerant with no SPOF or single point of failure. It is highly available. Machines, which are also called nodes, are logically organized in a ring architecture. Real-time read and write. Fast writes with tunable consistency. The level of consistency can be controlled among multiple nodes that contain data. Provides a simple SQL interface and interfaces similar to SQL to insert, update, and select the data. It is a key-value database. Each row of data has a primary key to identify the data. It is highly and horizontally scalable with thousands of nodes in a cluster. The image shows the Cassandra logo where the nodes are organized in a ring architecture. Apache HBase is another open-source NoSQL database. It is a distributed database with columnar storage that is built on top of HDFS. It provides real-time read and write random access to data. It supports large databases in the order of terabytes and petabytes. It is not relational and does not support SQL. Real-time big data refers to handling a massive amount of business data as soon as the data is created to get valuable insights and prescribe immediate actions. Here, real-time refers to an event that occurs. Using real-time big data tools, you can read and write data in real time, filter and aggregate in real time, visualize data in real time, process millions of records per second. Some use cases for real-time big data are as follows. A telecom provider wants to provide data plans to customers based on location. Here, the location data is received continuously and has to be processed in real time. A bank wants to indicate the ATM location based on customer location. Here, the customer location data is received in real time and a recommendation has to be made immediately. A car manufacturer can alert the car owner on any urgent maintenance required on the car based on the data provided by the car during driving. Measurement data of various sensors in the car has to be streamed to the car manufacturer in real time. A news channel may monitor breaking news items across the globe. Real-time news data from hundreds of sources has to be prioritized and selected for breaking news. A security system may monitor movements in a stadium during a game. Any suspicious movements need to be reported immediately. A telecom network provider wants to use the least congested network for each call. The decisions have to be made in real time. A credit card company wants to prevent fraudulent transactions. Here, probably both real-time and offline processing may be involved. A stock market application recommends stocks to buy every second based on the market conditions. Volatile market conditions have to be analyzed in real time. Here is a quick recap of what we have learned in this lesson. Big data is typically characterized by 3 V's. They are volume, variety, and velocity. The various data sizes used for big data include kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, and yottabyte. Apache Hadoop is the most popular framework for big data processing. It has 2 core components. They are Hadoop Distributed File System and MapReduce. Real-time big data refers to handling a massive amount of business data as soon as the data is created to get valuable insights and prescribe immediate actions. Kafka, Storm, Cassandra, Spark, and HBase are some of the tools to handle real-time processing of big data. This concludes Big Data Overview. The next lesson is Introduction to Zookeeper. Hello and welcome to Lesson 2 of the Apache Kafka course offered by Simplilearn. This lesson provides an introduction to Zookeeper. After completing this lesson, you will be able to describe what Zookeeper is and how it functions, and explain some of the common problems of distributed systems. You will also be able to illustrate the data model for Zookeeper and compare how the two types of Z nodes are different from each other. Furthermore, this lesson will help you discuss a few Zookeeper recipes and the way they handle some of the problems of distributed systems. Zookeeper is a coordination service of Apache that helps manage the activities of distributed applications. It is highly scalable. It also has an open source library of recipes for distributed systems, such as leader selection, exclusive locks, bookkeeper, and so on. These recipes facilitate building relationships between distributed processes and applications. One of the main features of Zookeeper is that it helps handle partial failures in distributed systems. Before you learn about Zookeeper, let us understand what distributed applications are and what sort of problems arise while using them. Distributed applications are run on multiple machines in parallel. They function by following the divide and conquer principle. This means that they divide large jobs into smaller jobs, which are then run in parallel on multiple machines. They are horizontally scalable if adding more machines reduces the execution time. For example, if 10 machines do a job in 10 hours, adding 10 more machines may halve the execution time by 5 hours. They are vertically scalable if increasing the memory, CPU, or other resources of each machine reduces the execution time. For example, increasing the memory from 100 gigabytes to 256 gigabytes may reduce the execution time of a job from 10 hours to 5 hours. The diagram shows 3 machines connected by a network switch. An application can be distributed to run on them in parallel. These machines are also referred to as nodes in a cluster. One of the major issues that crops up while using distributed systems is partial failure. Another common problem is a race condition. Deadlocks and inconsistent states are also some challenges of distributed systems. Let us look at each of these difficulties in detail. Partial failure is a major challenge in distributed applications. Suppose there are 2 nodes, Node 1 and Node 2, in a distributed system. Node 1 sends a message to Node 2 through the network. However, the network fails before Node 1 receives an acknowledgement from Node 2. As a result, Node 1 does not know if Node 2 got the message or not. It will know the actual status only after the network gets connected again. This is known as a partial failure in distributed applications. Though partial failures cannot be prevented, tools like Zookeeper provide a mechanism to handle them efficiently. A race condition takes place in distributed applications when multiple machines are waiting for one resource to become free. Suppose there are 4 different nodes in a distributed system. Let us assume that currently only Node 1 is using the resource, so it has an exclusive lock on the resource. All the other nodes from Node 2 to Node 4 are waiting for the resource to become available. When Node 1 releases the resource, Nodes 2 to 4 race to acquire the resource. Only one of them succeeds, while the others go back to the waiting state. This process continues till all the nodes get the resource. This is called a race condition. Deadlocks occur when there is a cyclic dependency on resources. The diagram illustrates a deadlock situation. There are 2 machines, Machine 1 and Machine 2. There are 2 resources, Resource A and Resource B. Machine 1 has locked Resource A and is waiting to lock Resource B. At the same time, Machine 2 has locked Resource B and is waiting to lock Resource A. Since none of the locks can be acquired or released, it leads to a deadlock. To resolve a deadlock, one of the processes has to be killed and redo the processing. Detecting deadlocks are generally CPU-intensive and expensive operations. Inconsistencies take place when changes are not propagated to all the machines in the distributed system. For example, let us consider a salary data which is initially equal to 100. This data is replicated to both the machines. The data is later updated to 200. This change is first propagated to Machine 1. The value stored on it is now changed to 200. However, due to some failure, this update is not propagated to Machine 2, so the value stored on it remains as 100. In such a situation, if a process A reads from Machine 1 while process B reads from Machine 2, Each process will get two separate values of the salary data. This leads to inconsistencies. Zookeeper helps coordinate distributed applications. It provides a very simple interface. It is expressive, which means that it provides basic blocks that can be used to build larger applications. It is also highly available and reliable. This is because it runs on multiple servers at the same time, so even if a few servers fail, it continues to function. To have a fault tolerance for in-machine failures, it is recommended to have two N+1 machines running the Zookeeper service. For example, if you want to have a fault tolerance of 3 machines, then you should have Zookeeper running on 7 machines. Another feature of Zookeeper is that it has loosely coupled interactions. Machines using it do not have to know each other. Zookeeper is actually an extensive library of recipes for distributed coordination. The Zookeeper data model consists of a hierarchical tree of nodes called znodes. The tree of nodes is similar to a directory structure in Linux. Each znode stores a small amount of data and has an associated access control list, or ACL. ACL represents which users can read, write, and/or update the znode. A znode can only store a maximum limit of 1 megabyte of data. The diagram here shows a tree structure of znodes. There are 2 znodes, /Kafka and /HBase at the root level. At the second level, there are 2 more znodes, /Kafka /node0 and /Kafka /node1. Zookeeper znodes can be of 2 types, persistent znodes and ephemeral znodes. Note that when a znode is created, its type is specified and it cannot be changed later. Persistent znodes are permanent and have to be deleted explicitly by the client. They stay even after the session that created the znode is terminated. Ephemeral znodes are temporary. These znodes are deleted automatically when the client session creating them ends. Ephemeral znodes are used to detect the termination of a client. Alerts, known as watch, can be set up to detect the deletion of the znode. Znodes can be sequential. To do this, you can set a sequence flag while creating a znode. The value of this flag is an increasing counter. The counter is maintained by the parent znode for sequential znodes. The sequence number is appended to the name of the znode. Sequential znodes are used to specify ordering of the znodes. In the diagram, you can see that under /Kafka parent, 3 sequential znodes, node 0, node 1, and node 2 are created. In a later lesson, you will learn how to install Zookeeper and Kafka on an Ubuntu Linux system. However, if you need to work on an operating system other than Linux, you can access the software provided by VMware. This software allows running one operating system on another using a virtual machine. This is facilitated by VMware Player. For non-commercial use, VM Player can be downloaded and used free of cost from the VMware website. Simplilearn has created a virtual machine on VMware Player. This machine, known as Hadoop Pseudo Server, comes with their pre-installed Ubuntu 12.04 LTS operating system and Hadoop setup. It can be opened with the VMware Player and can be used for installing Kafka. Hadoop Pseudo Server can be downloaded from the given link. PuTTY is a popular free tool for connecting to Linux systems from Windows through a remote terminal. It overcomes some of the limitations of the VM. For example, it allows moving the mouse pointer with ease, scrolling in the window, and copying and pasting text. PuTTY can be downloaded from the given link. WinSCP is a popular tool for copying files between Windows and Linux. It stands for Windows Secure Copy. It can be used to copy the files from the local Windows to the Ubuntu VM running in the VM Player. WinSCP can be downloaded from the given link. This demo will show the steps to install Ubuntu Virtual Machine or VM and connect with PuTTY. Download the VMware Player from the given link and double-click the VMware-Player-7.1.0-2496824.exe file to start the installation. The installation wizard appears with the welcome screen of the VMware Player setup. Click the Next button to continue the installation process. In the License Agreement screen, select the I accept the terms in the license agreement radio button after reading the full agreement. Click the Next button to continue the installation process. In the Destination Folder screen, choose the default location and click the Next button to continue the installation process. In the Software Updates screen, uncheck the Check for Product Updates on Startup checkbox. Click the Next button to continue. In the User Experience Improvement Program screen, uncheck the Help Improve VMware Player checkbox. Click the Next button to continue. In the Shortcuts screen, click the Next button to continue the installation process. In the Ready to Perform the Requested Operations screen, click the Continue button. The installation process will start. This will take a few minutes to complete. Once this is completed, click the Next button to continue. In the Setup Wizard Complete screen, click the Finish button to complete the installation. Start the VMware Player. In the Welcome screen, click the Open a Virtual Machine option to open an existing VM. Download and unzip the Hadoop sudoserver.rar file provided by Simplilearn. The extraction process begins. Open the VMware Player again and click the Open a Virtual Machine option. Browse and double-click the unzipped Hadoop sudoserver file. Note that the actual location may be different on your system. Open the Hadoop sudo distributed server.vmx file. Click the Take Ownership button. Click the Play Virtual Machine Play button to start the virtual machine. Click the I copied it button. In the Removable Devices pop-up window, select the Do Not Show This Hint Again checkbox and click the OK button. In the Software Updates window, click the Remind Me Later button to continue. When you get the login prompt, enter the login ID as Simplilearn and password as Simplilearn. Note that you can use the Ctrl+Alt keys to switch between the VM screen and the Windows screen. After logging in, enter ifconfig in the command prompt to get the network configuration of the system. Write down the IP address of the system as you will need it in the later part of the demo. Download PuTTY using the given link. Install and configure PuTTY to connect to the IP address saved earlier. Further, download WinSCP from the given link. WinSCP is a resourceful utility to exchange files between the Windows and Linux VM. You can install and configure WinSCP to connect to the IP address saved earlier. Run PuTTY by double-clicking the PuTTY-0.64-installer.exe file. In the security warning window, click the Run button. The welcome wizard appears. Click the Next button to continue. In the Select Destination Location window, click the Next button to continue. In the Select Start Menu folder window, click the Next button. In the Select Additional Tasks window, click the Next button to continue. Finally, in the Ready to Install window, click the Install button. In the Setup wizard, uncheck the View README.txt checkbox and click the Finish button. Open PuTTY. In the PuTTY configuration window, enter the host name with the IP address saved in the earlier part of this demo. Simplilearn at the rate 192.168.189.128. Select Simplilearn from the given options and click the Load button. Ensure the IP address is 192.168.189.128. Next, click the Save button to save the settings and the Open button to open a connection to the VM. In the PuTTY Security Alert window, click the Yes button. In the Login prompt, enter the user ID as Simplilearn and the password as Simplilearn. Congratulations! You have successfully logged into the virtual machine from PuTTY. This VM will be used to set up Kafka also in the later lessons. Note that multiple connections can be opened on the VM using PuTTY. This concludes the process of setting up and installing the VM. To install Zookeeper on the Simplilearn VM, first update the installation libraries. Then use the apt-get installer command to install Zookeeper. When prompted to enter a password, type Simplilearn, all in lowercase. Type Y if asked for any confirmation. To start the Zookeeper server, you first have to configure it. To do that, set up the directory permissions for Zookeeper. You can then start the Zookeeper server using the command given here. Note that the Zookeeper server listens on the port 2181 by default. Zookeeper installation comes with a command line interface. If you recall, 2181 is the default port for Zookeeper. The command line interface gives the following command prompt. The command line interface can be used to check the znodes and create new znodes. In the commands given here, the values 200, 201, and 202 are the data we want to associate with the znodes. The table shows the commands that can be used in the Zookeeper command line interface. The create command can be used to create a znode. The option -e is used to create an ephemeral znode. However, if you do not specify this option, a persistent znode is created. The option -s is used to specify a sequential znode. The help command is used to get information about the available commands. Path is the full path of the znode to be created and starts with a /. Some data has to be associated with the znode and is specified with the data. The ls command is used to list the znode directory tree. A path starting with a / is specified. You can also add a watch on the path to be alerted about any changes to the path. Get and set commands can be used to fetch the data of the znode or to update the data. Delete can be used to delete the znode at the path. Finally, you can use quit to exit the command line interface. Like the command line interface, Zookeeper also provides APIs that can be called from either Java or any other language. Zookeeper has different APIs to create znodes, add watches, getting and setting data, as well as to delete znodes. In addition, it also has APIs that can be used to get all the children of a znode and to check if a znode exists. There's also an API to synchronize all the znodes so that all of them have the same data. When a process is sending data to another process, it has to handle partial failures. Zookeeper provides a recipe to tackle such a situation. In the example given here, Process 2 is trying to send information to Process 1. The receiver creates an ephemeral znode with the same name as the session ID or process name. In this case, the znode is created with the name /process1. The sender keeps a watch on the receiver's znode. If the data reaches the receiver process successfully, it informs the sender and then deletes the znode. However, if process 1 fails, the znode is automatically removed. The sender gets an alert about this change through the watch. It then takes an appropriate action, such as resending the message. In this process, we use watches and the ephemeral character of znodes to handle partial failures. Let us now look at another Zookeeper recipe. Leader election uses ephemeral sequential nodes to create an automatic node order. Let us see how the three processes, Process 1, Process 2, and Process 3, use the leader election mechanism. Each process creates a sequential ephemeral znode under parent/Kafka with the prefix node. Thus, Process 1 gets the znode /Kafka/node0, Process 2 gets the znode /Kafka/node1, and Process 3 gets the znode /Kafka/node2. The znode with the least sequential value is chosen as the leader. Process 2 and Process 3 in turn become followers. So Process 2 watches its immediate preceding sequence number /Kafka/node0. Likewise, Process 3 watches /Kafka/node1. To automatically reorder nodes, the sequential property of znodes is used. If Process 1 completes successfully, it deletes the znode /Kafka/node0. This alerts Process 2 as it has a watch on the leader znode. Now Process 2 becomes the leader as it has the lowest sequence value. Process 3 remains a follower as the preceding znode is not modified. In this case, the watch feature serves to change the leader. This process helps you avoid a race condition. Note that only Process 1 and Process 2 are handling the leader change. However, if Process 1 dies before completion, then the znode /Kafka/node0 is automatically deleted as it is an ephemeral znode. This alerts Process 2 as it has a watch on the leader znode. Now Process 2 becomes the leader as it has the lowest sequence value. Process 3 remains a follower as the preceding znode is not modified. Leader election helps distributed processes to function by automatically handling a node failure. Here is a quick recap of what we have learned in this lesson. Zookeeper is a distributed coordination service. Partial failure is a major issue in distributed coordination. Zookeeper uses a hierarchical tree of znodes. Zookeeper has two types of znodes, persistent and ephemeral. Zookeeper provides recipes for handling common problems in distributed systems. Sequential property is used to order znodes. A watch can be set up to get alerts on changes to znodes. This concludes the lesson on Introduction to Zookeeper.